Hi, thanks for joining me today. I've got a fun problem from probability for you. This is all to do with expectation, and as we'll see, one of maths' favourite constants will pop up in the solution. So we have xi being a sequence of IID uniform 0, 1 random variables. So IID just means that they're independent and identically distributed. So we have a bunch of random variables, all of which are uniformly distributed on 0, 1. And we're going to let y be the random variable, which is the smallest value n, such that the sum from I equals 1 to n of xi is bigger than or equal to 1. So in other words, y is basically the first point at which, when we sum all the xi's, the first point at which that sum exceeds 1. We want to compute the expected value of y. So in other words, on average, how many of these xi's will we need so that their sum adds up to at least 1. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so there are probably a few different solutions to this problem, but the one I'm going to present is hopefully the easiest to follow. So we're going to start off by introducing a function, but it's actually, well, it is a function, but it's also a random variable. It's going to be y of x. So x here is just a non-negative real number. Now, before we had y being, the smallest n, such that the sum of the first n xi's is at least 1. This is going to be a similar thing, except where the sum is at least x. So it's going to be the minimum n such that the sum from I equals 1 to n of xi is bigger than or equal to x, like so. Okay, so what we want to do is work out the expected value of y of 1, but to do that, we're actually going to compute the expected value of y of x, work out what that is, and then just plug in x equals 1 at the end. Okay, so we've got y of x equals this guy here, and we want to compute its expectation, so the expected value of y of x, and perhaps the most obvious thing to do is to use conditional probability, so condition this guy based on the first value of xi. So this is going to be equal to the expected value of y of x given x1 equals, let's call it little y for now, and of course we've got to integrate this, or x1 here is uniform on 0, 1, so we're integrating between 0 and 1, and we've got a dy here. And now technically we have to multiply by 1 here, but of course that's not doing anything. This 1 here just comes from the probability density function of xi. Xi is uniform 0, 1, so its probability density function is just 1. So we have the expected value of y of x is just the integral from 0 to 1 of expected value of y of x given x1 equals y dy. I'm just going to get rid of this here. Okay, how do we get from this line to the next line? Well, let's have a think about this little y here. If this little y is already bigger than x, well then we're kind of done, because if little y is bigger than x, that means that x1 is already going to be bigger than or equal to x, so this y of x here would be 1. However, if little y is less than x, then we've still got a bit more to do. Expected value of y of x will be a bit bigger. So what we're going to do is split this integral and split it based on whether y is less than x or bigger than x. So this is going to be the integral from 0 to x of the expected value of y of x given x1 equals y dy, plus the integral from now x to 1 of the expected value of y of x given x1 equals y dy. Okay, so I haven't really done anything fancy going from this line. So this line I just split the integral into 2 bits. Now let's look at this guy first. So when y here is bigger than x, well then the expected value of y of x is just going to be 1, because if the first guy, y, is already bigger than x, then this thing here, or the minimum n, is just n equals 1, so that means we know that y of x would be 1, and thus its expected value would be 1. So for this integral here, I can just get rid of this and just replace it with 1. So this is just the integral from x to 1 of 1 dy, and that, of course, is just 1 minus x. So I can get rid of all of this and just replace it with 1 minus x, like so. For this guy here, I've got to think a bit more, because y now is less than x. So the first guy, the first xi, the first one, x1, is just y, but it's a little bit short of x. So perhaps if we draw a little number line, that might help us. So we've got 0 here, say x is here, and our first guy is y, it's less than x. So this is kind of our first x1. It only takes us that far. And now we want to know how many xi's is it going to take us to get from y to x. But that's kind of similar to what we've already done. It's except now instead of y of x, it's going to be y of x minus y, this smaller distance here. How many xi's is it going to take us to get from there to there? Well, that's exactly capital Y of that distance there, which is little x minus little y. So this thing here is going to equal, let's bring this 1 minus x here, 1 minus x plus the integral from 0 to x of this guy here, which is the expected value of x minus y. And now we've got to add on 1. I'll explain why in just a second. The reason we've added on 1 is because, well, we already know that this x1 took us this far to y. So we know that we've already kind of used up one of the xi's to get from here to here. And now what we've got left is just x minus y. And that's kind of encompassed into this bit here, this expected value of y of x minus y. So that's expected value of y of x minus y plus 1 dy. And yeah, this plus 1 is for the first x1, and then what's left is going to take us this distance here. So we have the expected value of y of x is just 1 minus x plus the integral from 0 to x of the expected value of y of x minus y plus 1 dy. But this plus 1 here, when I integrate it, that's just going to give me an x. So I can get rid of this here and then add on an x. But this minus x and that x there cancel very nicely. So I've just got the expected value of y of x is 1 plus the integral from 0 to x of the expected value of y of x minus y dy. We're almost done in solving this problem. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that the expected value of y of x is simply 1 plus the integral from 0 to x of the expected value of y of x minus y dy. Now what we're going to do is use this to compute the expected value of y of x. Well, let's just change this guy here just for notation to e of x. So the expected value of y of x was just denoting with e of x is equal to 1 plus the integral from 0 to x of e of x minus y dy. Let's just do a u substitution on this. We're going to do u equals x minus y. So that just gives us that du is equal to minus dy. So this right-hand side here just becomes the integral, 1 plus the integral from 1, y is 0, u is going to be just x. And when y is x, u is going to be x minus x, which is 0, of e of u dy, which is minus du. So minus goes here, du. But we can use this minus sign here to flip the limits of integration. So get rid of the minus and swap these round. So we get e of x is 1 plus the integral from 0 to x of e of u du. This is just a lovely integral equation. The way we can solve it is just differentiating both sides. To take the derivative of the left-hand side, we get e prime of x. Take the derivative of the right-hand side, we just get, well, the derivative of 1 is 0, and the derivative of this guy here, by one of the fundamental theorems of calculus, is just going to be e of x. So e prime of x equals e of x. What is e of x? Well, this is just a very basic kind of thing from differential equations. Hopefully you've seen it before. We just get that e of x is some constant a times e to the power of x. So e of x, which is just the expected value of y of x, is just some constant a times e of x. And of course, we want to quickly work out what this constant a is. And the way we're going to do that is just by plugging in x equals 0, or technically x equals some really, really small positive real number. So when x is a really, really small positive real number, how many of the xi's do we need so that the sum is bigger than 0, or this really small positive number? So let's just use 0, so I'm not getting lost. So the expected value of y of 0, well, from this guy here is just going to be a times e to the 0, so just a. But what is y of 0? It's the fewest number of x's we need so that the sum of the xi's is bigger than 0. Well, just one xi will do then. So just take the first one because we know it's going to be some number between 0 and 1. So then e of y of 0 is just going to be 1. So we get that a is equal to 1. So that tells us the expected value of y of x is just equal to e to the x. And this in fact solves a more general problem, but remember we wanted to work out the expected value of y of 1, so of course that is just equal to e to the 1, which of course is just e, like so. So if you have a uniform random variable on 0, 1, and you want to know how many on average times will it take you to get a sum bigger than 1, on average it will take you e times. And it's quite nice to see that e pops out, and it pops out relatively naturally. When you just look back at the maths that we've done, it's not too surprising that e should pop out. Anyway, I hope you have enjoyed this. Thank you for watching, and I'll catch you in the next one. Have a great day.